In the previous lecture, we started the discussion on the topic of RF coupling, and therein we discussed how this coupling phenomena is essentially rooted in the basic principles of electromagnetic induction. To revise that, to reiterate the coupling concept, coupling is nothing but the phenomena of a current carrying wire where the current is time varying being able to introduce another current in another conductor, which is originally not being powered through any sort of source. That is coupling. So the coupling, as I said, is essentially dependent on the principle of electromagnetic induction. And what we saw in the previous lecture was a pair of conductors. Let us say we look at the top view of a pair of coupled lines. So we had two metallic conductors which are kept in close proximity, as we discussed. For the magnetic field to make any effect, the conductors must be kept in close proximity, and let us say there is a ground also in the bottom layer. These conductors are on the top layer of a PCB, making them a microstrip configuration, whereas there is a ground on the bottom. There is a ground on the bottom layer. So let us say we saw that essentially now, because of the mutual connection between the two conductors, if not physically then electromagnetically, we cannot treat these conductors independently. But then again, we said that under certain conditions we can indeed treat them as independent conductors. So therefore we had applied two things. One is the even mode, the other is the odd mode. We had applied these two criteria for analyzing this pair of lines. Okay, so essentially what we saw, to draw this in an electrical equivalent, let us say there are two transmission lines. This is line 1, the other is line 2. Let us say, without loss of generality, that the bottom conductor is ground. So essentially these are two transmission lines which are kept close to each other. So what we are seeing, or what we saw, was that in the even mode we could treat each line independently and say that each line has a characteristic impedance called as Z0E, which is equal to under root of L by C, where L and C are the per unit length inductance and capacitance respectively of each of these lines. So we will assume that each of these two transmission lines, or each of the conductors, essentially are the identical to each other or the same as each other. And in the odd mode is when there are two currents which are equal in magnitude, or two waves which are equal in magnitude but opposite in direction or phase in the conductors. So over there we said that although there exists a mutual capacitance between the two lines, we could essentially isolate the two capacitances, or isolate that mutual capacitance to reflect on each of these conductors, and therefore again we could treat them independently by saying Z0O in the odd mode is equal to under root of L by C plus 2Cm, where Cm is the per unit length mutual capacitance. Now let us say the proximity between the two lines happens only for this length. There is some length L, or electrical length theta. Only for this particular length the lines are running close to each other. So then what we can say is that what effectively this looks like is, if we were to connect transmission line on each of the ends, let us say one over here, another over here, just to indicate that these portions of lines are not close to each other. So I can essentially say that this entire coupled line structure looks like a 4-port network. Let us say this is port 1, this is port 2, this is port 3, and this is port 4. Effectively, what we have is a pair of lines running close to each other, and therefore we can treat this as a 4-port network. Right? So, well, if we have a 4-port network, just like 2 and 3-port networks we've been analyzing so far, we have to also learn how to analyze this kind of a network. So therefore, let us say each of these lines which are not in proximity with the other conductor, let us say that each of these have characteristic impedance Z0. The portion of the lines running close to each other, they need not be Z0, because they have to be analyzed using two values of Z0. One is Z0E and Z0O, because they are correlated to each other, whereas these sections are not. So this kind of a 4-port network where the coupling is happening, this device is called as a coupled line directional coupler. Coupled line means the lines are in close proximity and their currents depend on each other and the field linkage between the two. Why directional? Is because of electromagnetic induction, as we discussed. If the current in the first conductor is in this direction, the induced current in the second conductor will be in the opposite direction. So therefore the direction is quite important. So that's why the word directional coupler. So as we discussed, one possible application of these is in probing transmission lines, where physical connection of voltage probes or equipment to the line is not possible due to loading and power division. So just by sampling a small portion of the power from the main line, we can back calculate what is the power or the wave magnitude in the main line, and that is very, very useful in measurements. Right? So again, what we will do, we will redraw this. We will redraw this coupled line directional coupler, but without showing the ground conductor. Just like how we did for a Wilkinson, we will only look at the top view. We will just assume that the ground conductor is there. So these are the two conductors which are in close proximity. Port 1, port 2, port 3 and port 4. And let us say each of the lines have a electrical length of theta, where theta is beta times L. Now the question is, can we derive the S matrix of this 4-port network? So since the network has 4 ports, the S matrix will also be a 4x4 matrix. So therefore, now let us again apply the even and odd modes, but from an external perspective. So let us first say we will look at the even mode, and then we will look at the odd mode. So in the even mode, we assume that there are two waves, two identical waves which are flowing from left to right. And we will assume, for the sake of convenience, that two sources are connected, one at port 1, the other at port 3. So what it looks like would be something like this. So one source over here, the other source over here, and we will assume that the other ports are terminated using a matched impedance Z0. That is what we assume. So let us say each of these voltage sources is Vs. So this Vs essentially enters in each of the conductors. So if a wave is entering, it's very much possible that there will be some reflection. So let's call this reflection coefficient as gamma E in the even mode. Since the conductors are identical, even this one will be gamma E. And what is reaching each of the loads, let's call it as a transmission coefficient. One is TE, the other is also TE. Whereas in the odd mode, it will be the same structure, the two coupled lines, and this time, however, the sources will be of equal magnitude but opposite polarity. So one will be Vs, the other will be minus Vs. And the terminations at ports 2 and 4 don't change, they will continue to be Z0. So therefore, in this case, the reflection coefficients, let's call them as gamma O and gamma O to signify the odd mode. And the transmission coefficients, let's call them as TO and TO to account for the odd mode. Is this fine? Now what we need to do? We need to superimpose the two. The even and the odd modes. So the total input voltage at port 1. So the total input at port 1 will be the algebraic sum of the even mode input and the odd mode input, each of which is Vs. So therefore it will be 2 Vs, just the addition of the two. Then what is the total reflected voltage at port 1, or total, let us say, outgoing at port 1? So in the even mode, it will be gamma E times Vs, and in the odd mode, it will be gamma O times Vs. So totally there will be gamma E times Vs plus gamma O times Vs. Right? So what we are essentially seeing is that for input at port 1 at 2 as 2 Vs, the output or the outcoming wave or the reflected wave at port 1 is this. So therefore I can say that the reflection coefficient at port 1 that is nothing but the outcoming voltage divided by the incoming voltage. So therefore it is nothing but gamma E plus gamma O by 2, because Vs and Vs will get cancelled. That's all there is. So therefore, using this, which is nothing but the S11, because reflection coefficient at port 1 means input at port 1, output at port 1. So using this similar analysis using the even and odd mode, we can define the remaining S parameters with respect to port 1, that is S21, S31 and S41. What will they be? So S21, the even mode and odd mode, the even mode transmitted voltage will be TEVS and this will be TOVS. So with respect to port 1, it will be TE plus TO by 2. What about S31? So the output at port 3 now will be gamma EVS minus gamma OVS because of this minus sign. So therefore, S31 will be gamma E minus gamma O by 2, and likewise S41 will be TE minus TO by 2. Right? So now, because this is a 4-port device, and we can say that each of the ports is symmetric. So as if we calculate with respect to any one port, we can apply the similar logic for other ports also. So if I can say that how I am calculating S11, the similar way I can calculate S22, S33 and S44. There is absolutely no difference. So therefore, what do I want? S11 indicates the reflection coefficient at port 1, and as always, we will try to ensure that S11 must be matched. Which indicates S11 should be 0. So, this is one requirement. So, if S11 is 0 and we put it over here, what it means? That means gamma E plus gamma O should be equal to 0. Right? Next, if we look at this coupled line structure, we had said that if there is a wave which is starting from port 1 and it's going towards port 2, the induced wave will be here and it will travel to port 3. That means ideally there should be nothing coming to port 4. Because of the nature of the induced current or the induced wave being opposite to the main wave, that whole wave should be absorbed at port 3 and nothing should come to port 4. So therefore, for input at port 1, port 4 will get 0 power. So therefore, port 4 is called the isolated port. And because of that, this S11 is also 0. That means TE minus TO is also 0. This is what we need. So this is the isolated port. Because the coupled wave is now going to port 3, port 3 is called as the coupled port. And port 2, well, most of the input wave is supposed to come to port 2, so therefore it is called as the through port. All these definitions are valid for port 1 as an input port. Alright. So, in this case, what we can do is that we have essentially got two equations, but that is not giving us too much of a headway. We still don't know what is S21 and S31. So for that complete knowledge, we need to find out what is gamma E, gamma O, and what is TE and TO. So once we know what is gamma E and gamma O, we can find out S11 and S31. Once we know what is TE and TO, we can find out S21 and S41. Although we want to make sure that S11 and S41 are both 0, that would require certain values for S21 and S31 also. So therefore, the analysis is not all that simple as one may have hoped for. So what happens over here now is that we need to look at this analysis in a little bit more detail. So therefore, what we do, we will go back to the definition of the coupled line coupler, which was something like this, which had two conductors which are in close proximity. We had said, although electromagnetically that they are dependent on each other, we were indeed able to ensure that we could treat each line independently thanks to the even mode and the odd mode. So therefore, consider only the top conductor. Top conductor means the conductor connecting ports 1 and 2. Connecting ports 1 and 2. So here what happens? If I look at this and treat it as a transmission line, it would look something like this. Port 1 and port 2. What would be the characteristic impedance? There is no single characteristic impedance. It could have Z0E, it could have Z0O, depending on which mode it is being operated in. Now, to analyze and get the S parameters, what we will do over here, since it's a two-port network, we will try to first obtain its ABCD matrix or the transmission matrix. Okay? So, let us say if you have a transmission line, this is port 1 and port 2, which has some characteristic impedance Z0. Suppose. And its electrical length is some theta equal to beta L. What would be the ABCD matrix of this transmission line? What would be the ABCD matrix of this transmission line? Well, we know that the transmission matrix is defined in this way. If you assume that the I is in this direction, how can you do this? Well, you can do this by starting with the voltage and current equations on the transmission lines. As a result of the solution, which we had discussed in the start of the course, you can do that. There are other ways too. You can write these and then substitute different values of L. In that case, you would see that the transmission matrix would come out to something like this. The technique can be anything, but for a transmission line of length, electrical length theta and characteristic impedance Z0, you get the ABCD matrix is cos theta, JZ0 sin theta, JY0 sin theta and cos theta. This is the ABCD matrix. So now, if we come back to the top conductor of our coupled line, it has two characteristic impedances, Z0E and Z0O, and let us call the electrical length as theta. So obviously, because there are two values of Z0, there will be two matrices for this line, one in the even mode and one in the odd mode. So therefore, just by using this result, you can prove it yourself, and you can apply this to show that the even mode ABCD matrix will be cos theta, JZ0E sin theta, JY0E sin theta and cos theta. And in the odd mode, it will be just an extension of this, JZ0O sin theta, JY0O sin theta and cos theta. Right? Obviously, here Y0E is 1 by Z0E and Y0O is 1 by z0 o. So therefore, what we can do now is we can get the reflection coefficient for each of the modes. So let us say gamma E and gamma O indicate the reflection coefficient in each mode, and TE and TO indicate the transmission coefficients in each mode. So therefore, we will apply the formulae that we know to convert ABCD parameters into reflection and transmission coefficients, or the S parameters. We will not write them as S parameters because we are not denoting now for the whole 4-port network, but rather we will talk only about the reflection and transmission coefficients, which are nothing but a subset of the S parameters. So therefore, if you recall, gamma E will be AE minus DE, where AE, DE, BE, CE are the even mode ABCD matrix coefficients. And Z0 will be the impedance of the feed lines. And so on. Like this you can get for gamma O, TE and TO. You can write this. I will not write this for yourself. What we need essentially is, let us apply the first requirement. Let us apply the first requirement of getting S11 equal to 0 needed. And we had derived for this to work out, gamma E plus gamma O must be equal to 0. So then let's apply this gamma E plus gamma O and see under what condition it will become 0. This will be AE minus DE plus BE Y0 minus CE Z0 divided by AE plus DE plus BE Y0 plus CE Z0 plus AO minus DO plus BO Y0 minus CO Z0 divided by the sum of all of these So we know that A and D are equal to each other from that previous matrix, so these will get cancelled. So what we will now get is, if you substitute, you will get J Y0 Z0 E sin theta minus J Z0 Y0 E sin theta divided by cos theta plus cos theta will be 2 cos theta plus J Z0 E Y0 sin theta plus J Y0 E Z0 sin theta plus J Y0 Z0 O sin theta minus J Z0 Y0 E sin theta divided by, again 2 cos theta will come, plus J Z0 E Y0 sin theta plus J, it will be Z0 O, yes, Z0 O plus J Y0 O Z0 sin theta. So So now you can immediately notice that solving this huge equation is going to be very tedious. Now, one thing that we could do to simplify it a bit is that we could try and make the denominators equal. We could try and make the denominators equal. So making the two denominators equal, what we will get is essentially this. This will be equal to 2 cos theta plus j z0 o y0 sin theta plus j y0 o z0 sin theta. This term and this term will get cancelled. So what we will essentially get after cancelling these two is that even the sin theta terms will get cancelled. So what we will have left behind is only this z0e y0 plus y0e z0 will be equal to z0o y0 plus y0o z0. So let us now convert all of this into impedance terms. This will be z0e by z0 plus z0 by z0e. This is equal to z0o by z0 plus z0 by z0o. Alright. So what we can do is we can group the terms where z0 is on the numerator separately and the terms where z0 is on the denominator separately. So therefore we will bring this one over here and this one over here. So what we will get now would be z0e minus z0o divided by z0 would be equal to z0 times 1 minus z0o minus 1 minus z0e. I think this is what we will get. So if you now combine the two, you will get z0e minus z0o divided by z0o times z0e. And this will be equal to the left hand term z0e minus z0o divided by z0. We can see these two terms are the same. So this entire thing will be cancelled. This entire thing will be cancelled. So this shows that z0 square should be equal to z0o times z0e, which means z0 must be the geometric mean of the even mode and odd mode impedances of the line or of the coupled pair of lines. This is a very, very important result. This is needed to make the denominators of that huge equation quite easy. Now what we can do is the following. Now that the denominators of this huge expression are now the same, we can simply add the two numerators. So putting this into gamma e plus gamma o equation and adding the numerators, what we will get is the following. J y0 z0e sin theta minus j z0 y0e sin theta plus j y0 z0o sin theta plus j z0 y0o sin theta. So what we can do is, again we will convert these in terms of impedances. Which will be now j z0e by z0 sin theta minus j z0 by z0e sin theta plus j z0o by z0 sin theta plus j z0 by z0o sin theta. So we will now put this condition over here, that z0 must be equal to the geometric mean of these two. So wherever z0 is, we will substitute. So then what we will get is this: z0e by z0o root times sin theta, the j will be there, minus j z0o by z0e sin theta plus j z0o by z0e sin theta minus j z0e by z0o sin theta. What we are seeing is that these two cancel out and these two cancel out. So therefore this is 0, which means that S11 is 0 always. This is an extremely important result. S11 will be equal to 0 always as long as Z0 is equal to Z0e, Z0o. That is the condition for making the denominators of those huge terms the same. Now, what does this mean? Even if S11 is 0, we know that there is a, it may not sound all that surprising or important. What you must notice is there were the sine theta terms also. So what we are seeing is, as long as we are able to ensure that the Z0 is equal to the geometric mean of Z0e and Z0o, S11 will be 0 irrespective of theta. So what does this mean? The lines can be really long, the lines can be really short, or the frequency can be anything. But the important thing is that all the ports, in particular S11, that is port 1, will be always matched irrespective of the theta, that is length or frequency. Because as you know, theta can be changed by changing either the length or the frequency, right? So this is an extremely important result, which shows that no matter what the frequency is, the S11 will always be 0. If you notice, in case of the Wilkinson power divider, that was not the case. Although we did not discuss it in too much of detail, there were those two arms, each of lambda by 4. And the moment you have a lambda by 4, you have a constraint on the frequency. So that we had proved some values for the S11, S21, S31. They were only at the frequency where the physical length of those two arms would be equal to the quarter wavelength of the wave that is flowing. So therefore, the Wilkinson is also a narrowband device. But here S11 is 0. That means it is matched for a very broad range of frequencies, ideally infinite. Now, the other S parameter what we wanted was S41. This is the isolation parameter for input at port 1. Port 4 should not receive any signal whatsoever. So what we can see is that S41 what we got was TE minus TO by 2. So again, if you apply this same criteria into the TE and TO equation, you can put that this is 0. So this you can prove very easily yourself. I shall not show it over here. So that is what is very important. That means S11 and S41 are 0 irrespective of frequency or length. This is a very important advantage that is provided by the coupled line directional coupler. Now, this analysis is not complete. This analysis is not complete. It's not complete because we do not know what is S21 and S31. So we had said, let's look for S31, that is equal to gamma E minus gamma O by 2, and S21 is TE plus TO by 2. We had derived this. So now, if you substitute the ABCD parameters over here and again apply the condition for Z0 becoming equal to under root of Z0O times Z0E, what you will see is that S31 essentially looks like this: J sine theta. It's just a simple steps of some mathematical operations. You can look at it yourself. This is what you get. So now you can see it is not all that simple. Now the S31 is indeed a function of theta and the impedances also. So what this means is that while we were able to achieve S11 and S41 as 0, S31 indeed is a function of theta. Or why of theta? Because theta is the variable. Usually these Z0E and Z0O are pre-decided. So what we are seeing essentially is that S31 is a function of theta. So now if we look at S21, again if you apply the ABCD matrix parameters and substitute over here, you will get that S21 is this quantity, 2 divided by 2 cos theta plus j sin theta times this. So again, this is also a function of theta. So this is a very important result. While S11 and S41 we have maintained are both 0, the S21 and S31 however, that is the through port transmission coefficient and the coupling coefficient, these are not so straightforward. These will be functions of theta. Okay, so what we will do now? What we will is we will take some different values of Z0E and Z0O, and then we will try to apply those values and see what we are getting as the values for, let us say, any of these parameters. Let us say S31. So let us consider one case. Let us say Z0 is 50 ohms. We had proved in the last class that Z0E is always more than Z0O. So let us say we take two values, one for Z0E and one for Z0O. Let us call this as case 1. So let's say Z0E is 86.73 ohms and Z0O is 28.83 ohms. You can verify yourself that the geometric mean of these two will be equal to 50 ohms. I have pre-calculated these values, and if I now plot the magnitude of S31 in dB, that is minus 20 log 10 of mod of S31. Sorry, I'll not say minus, I'll keep it as plus itself. So therefore what we will see is something like this. If I plot mod of S31 as a function of theta in degrees, sorry, in let us say radians, what we will see is something like this. So over here, the maxima will be somewhere around minus 60, and the maxima will happen at theta of pi by 2. You can verify this yourself. If you put theta as pi by 2, the cos term will become 0. So therefore, the sine term will become 1 and you will be left with a real quantity which will be the maximum magnitude. This is for case 1. Let us take case 2. Case 2 is Z0E is 69.37 ohms and Z0O is 36.04 ohms. Again, you can show that the geometric mean of these is 50 ohms. So what you will see is again something like this. We will call it as, this is case 1, this is case 2, and the magnitude over here comes out to be around minus 10 dB. Let's take one more case where Z0E is equal to 59.84 ohms and Z0O is 41.78 ohms, and let's call it as case 3. Over here, you will see that this curve goes like this. Minus 15 dB. Right. So this is what we get for the different cases. Now, this is something very interesting to note. More is the difference between Z0E and Z0O, more is the power that reaches port 3. And closer are the values of Z0E and Z0O, lesser is the power that goes to port 3. So therefore, if you want the coupling to be very tight, that means the induced wave in the second conductor, you want it to have a much high magnitude, then the values of Z0E and Z0O must be really far apart, as far apart as possible. For example, case 1. And if you are okay with inducing even a weak wave in the second conductor, a wave of small magnitude, you can keep the values of Z0E and Z0O close to each other while maintaining Z0E is more than Z0O for the same Z0 value, which is nothing but the geometric mean of the two even mode and odd mode impedances. So in today's lecture, we looked at how to apply the even and odd mode to analyze and obtain the S parameters, the reflection coefficient, transmission coefficient, etc. for a coupled line directional coupler. We will continue from this point onwards in the next lecture. Thank you.